Now that I've told you about the periodic table of the elements, which systematizes all the known chemical elements, we're ready to begin our exploration of chemistry. Lecture 21 introduces this rich subject of chemistry by focusing on the most basic principle of chemistry, that atoms combine by rearranging their electrons. In the course of this lecture, we'll see that the richness of the materials in our world are formed by three primary kinds of bonds. The ionic bond, in which one atom gives up an electron to another, thus forming ions. The metallic bond, in which a whole group of atoms gives up electrons to form a negative C of charge. And finally, covalent bonding, in which several atoms, a small group of atoms, share electrons in order to achieve a stable state. In this lecture, I have two main objectives. First, after a brief review of the periodic table and Mendeleev's great work, I want to explore with you the underlying causes of chemical bonding. Why should electrons bother to rearrange themselves to form chemical bonds? And as we shall see, as in so many of the natural phenomena we've discussed, it has to do with energy, the effort of a system to achieve its lowest energy state. Then we're going to examine in some detail the three common strategies that electrons employ when they rearrange to form chemical bonds. That is, ionic bonding, metallic bonding, and covalent bonding. Well, first, let's review the periodic table of the elements. This table systematizes all the known elements, and it was the great discovery of Dmitri Mendeleev, the Russian chemist, who, along with his contemporaries, knew about 63 different chemical elements. This was in the mid-19th century. Now, Mendeleev and his contemporaries knew that 63 elements were far too many to be fundamental particles. After all, how could you have 63 different fundamental building blocks of the natural world? They assumed there had to be some underlying order, some underlying pattern, and so Mendeleev applied the scientific method. He said, I have 63 data points. Those are the 63 chemical elements. First, I'm going to search for a pattern. I'm going to look for some kind of underlying order. Then we'll see if we can make a hypothesis, a prediction, which ended up being the periodic table of the elements, which finally made predictions which could be tested. That was his strategy. He saw the patterns in the chemical elements, as did many of his contemporaries, because groups of elements showed such similar behavior. For example, the alkali metals, lithium, sodium, potassium, all silvery metals, all soft, all highly reactive. In fact, they all would react violently with water. We had the halogens, fluorine, chlorine, bromine, iodine, these elements that are all nonmetals. In fact, they're gases and liquids, very corrosive, very reactive. The halogens all react in 1-to-1 ratios with the alkali metals. And there were other groups, the alkaline earth metals like magnesium and calcium and barium. Once again, similar chemical properties amongst themselves and very different from the other elements that were known. Mendeleev seized on these patterns, and he also seized on the fact that elements have different weights. You can order the elements from left to right by increasing weight, hydrogen being the lightest element and increasing and so forth. And so he arranged his table with vertical columns of elements that displayed similar properties left to right according to increasing weight of the elements. This led to the great periodic table of the elements. And the periodic table was great not just because it systematized the known elements, but because it made predictions, as all good scientific hypotheses must. It predicted elements that had not been seen, and lo and behold, those elements within a few years were discovered. This was the great triumph of the periodic table. The fact is, though, elements don't occur in isolation in nature. You don't find single isolated atoms. What you find is atoms in combination. For example, water, it's H2O, two atoms of hydrogen combining with one atom of oxygen. We have window glass that contains primarily silicon and oxygen combined in a 1-to-2 ratio, SiO2. And even the air we breathe is composed of atoms in combination. Oxygen, O2, two oxygen atoms bound tightly together. And 80% of the atmosphere is made of nitrogen, N2, two atoms of nitrogen bound together. So why should this be? Well, one reason lies in the fact that there's such stable arrangements of electrons, the magic number of electrons that we've seen, 2 electrons, or 10 electrons, or 18, or 36, and so forth. These are the magic numbers of electrons, and they correspond to filled shells of electrons in Mendeleev's periodic table. The first row has 2 elements, so a filled shell has 2 electrons. The next row has 8 electrons. So 2 plus 8 gives you 10, the magic number when you have 2 filled shells. The third row has 8 more electrons, leading you up to 18. So 2, 10, and 18 are these magic numbers. So on to our first topic of the day. Why do atoms bond to each other? The key to understanding why atoms link together is energy. All natural systems tend to adopt a state of lowest energy. Water flows downhill from high energy to low. Electrons in a battery move from the negative terminal to the positive terminal to achieve a state of lower energy. Indeed, heat, if you have a hot object, the heat flows outward in all directions to achieve a state of lower energy. And electrons are no different. I want you to imagine a situation of a steep-walled valley strewn with boulders. And this will be an analogy to electrons themselves. Imagine that you're driving down a road at the very floor of the valley, and to either side of the road are giant boulders that are perched just on the side of the roadway. They're on the valley floor, though. They're all the way down at the lowest possible energy state. Now, you could move those boulders up to the side of the valley if you wanted to, but it would take a lot of work. You'd have to exert a lot of energy. But there are also boulders that are perched in depressions and ledges on the side of the valley, and some boulders all the way up at the very tip top of the rim of the valley. Now, those boulders have a lot more energy. If there were an earthquake or if someone came along and pushed them off, they'd come crashing down, and they'd release their gravitational potential energy, turn that into heat, as they did destruction when they landed on the valley floor below. Well, electrons are very much the same. The arrangement of an atom's electrons are, in fact, exactly analogous to positions of boulders on a valley. Now, if we go to the periodic table and look at the extreme right-hand column, you'll see the inert gases. These are atoms that have completely filled outer shells, helium with 2, neon with 10, argon with 18, and so forth. These elements are extremely stable because they have the lowest possible energy, analogous to boulders on the valley floor. Nothing you can do is going to make those atoms more stable. And so the inert gases exist in nature as isolated atoms in the gas. They never bond to anything because there's no reason for them. They wouldn't want to gain electrons. They wouldn't want to lose electrons. Well, now think about the atoms that are slightly off that magic number. Once again, looking at the periodic table, one has the halogens, like fluorine and chlorine and bromine. These elements have 1 too few electrons, 9 instead of 10, 17 instead of 18. And so the halogens are desperate to gain an electron. As a result, when they do, they release huge amounts of energy, sometimes in a flash, sometimes in an explosion. This is like a boulder perched right at the very top of the valley coming crashing down, releasing its energy. By the same token, one can look all the way over in the left-hand column of the periodic table at the alkali earth and the alkali metals. For example, the first column with lithium, sodium, and potassium. These are elements that desperately want to get rid of an electron. Sodium has 11 electrons. It wants to have 10. Potassium has 19. It wants to have 18. And so these elements try to get rid of an electron. And again, when they do so, it's like the boulder crashing down from the highest part of the valley. Now, the rules of electron arrangements may seem quite arbitrary. Why should 2 be stable? Why 10? Why 18? Why not any number, 3, 4, 5? Indeed, why should we even have a difference in numbers? Well, I want you to imagine what would happen if all the different combinations of electrons had exactly the same energy. In that case, the world of chemistry would be exceedingly boring because every electron arrangement would have equal energy. It would be like a flat, featureless plane in which boulders are strewn about, but there'd be no incentive for those boulders ever to move. If there's an earthquake, they're just going to stay put. They're not going to release energy. So, in a sense, the reason that we have chemistry is because they're magic numbers, and if we didn't, we wouldn't be here talking about why they're chemical bonds. Well, now let's look in some detail at the three common strategies that atoms adopt to form chemical bonds. These three types are ionic bonding, metallic bonding, and covalent bonding. And we're going to begin with ionic bonding. Now, in thinking about ionic bonding, the key is to remember that atoms or molecules with magic numbers of electrons are particularly stable, while atoms or molecules that are one or two electrons too many or too few are very unstable. Let's look at the periodic table. Chlorine, element 17, for example, has one too few electron. It wants to have 18, but it only has 17. It'll do almost anything it can to gain that electron. By the same token, sodium, which is element 11, has one too many electron. And it's going to do almost anything it can to lose an electron. So I want you to imagine what happens when a chlorine atom meets a sodium atom. Well, naturally, the sodium says, here, take my electron. I don't want it. And so the sodium's happy. It has 10. Chlorine's happy. It has 18. And something else happens in the process. When the chlorine gives up that electron, it now has 11 positive charges in its nucleus, but only 10 electrons. So it's a +1 ion. And the chlorine, it has 17 positive charges in its nucleus, but now it has 18 electrons. So it's a -1 ion. You have a +1 ion, a -1 ion. They see each other and they say, aha, electrostatic attraction, and they bond. This is the formation of an ionic bond. And indeed, we see this type of ionic bond in many kinds of common materials. For example, sodium chloride, table salt. Whenever you have an alkali metal like sodium that meets up with a halogen like fluorine or chlorine, you form a salt. But the positive and negative ions attract each other, and so you get the bond. Now, because these bonds are between two ions, it is called the ionic bond. There are many examples. Epsom salt is an example. Most rocks are examples. Many of the ceramics that you see in your day-to-day life are formed with ionic bonds. And there are many examples from the periodic table. If we go back to the periodic table, you can see that all of the elements in the first column, the alkali metals, will bond in a 1-to-1 ratio with all of the elements in the next to the last column, the halogens. Sodium chloride is the most common example of these, but there are many others. For example, when you buy salt, you'll often notice that it's called iodized salt. That's because we need a small amount of iodine in our diet to help the thyroid gland. If we don't get it other ways, we can get it from table salt. Because in addition to having sodium chloride, table salt typically has about 1/100% of potassium iodide, another one of these alkali halides. And that's because potassium in the periodic table, in the first column, bonds with iodine, the halogen, in the next to the last column. There are many other kinds of ionic bonds. If you look at the second column of the periodic table, you see the alkaline earth metals. That includes magnesium and calcium and so forth. And the bonding strategy here is clear. Each of these elements wants to get rid of 2 electrons. Calcium, for example, is element 20. It wants to get rid of 2 electrons so it can get down to the magic number of 18. Its strategy when it comes across fluorine is to say, here's 2 electrons, and 2 fluorine atoms come along and take up those electrons. You get calcium difluoride, CaF2, which is the beautiful mineral fluorite. Fluorite forms large crystals. They're often purple, and very beautiful specimens can be found around the world. Fluorite, in fact, is the commonest mineral of the element fluorine. Let's recall the bonding strategy of fluorite. Calcium, element 20, loses 2 electrons to achieve a filled shell arrangement of 18 electrons. And it gets a +2 charge. And then 2 fluorines gain an electron, and each of them becomes a -1 charge. Now, one of the most common types of ionic bonding in nature links silicon, which is element 14, and oxygen, element 8. On the periodic table, you'll see that silicon, element 14, then wants to lose 4 electrons and become a +4 ion, while oxygen, element 8, wants to gain 2 electrons and become a -2 ion, forming a strong ionic bond between one silicon and 2 oxygens. This is SiO2. This ionic SiO bond is particularly strong because it links a +4 ion with a -2 ion. Now remember Coulomb's law, this is from lecture 11, which described the force, the electrostatic force between 2 charges. The force is proportional to the product of the charge on the first object and the charge on the second object. In sodium chlorine, those charges are +1 and -1, so the relative strength of the bond is 1 times 1 or 1. But in silicon oxygen bonding, the relative strength is 4 times 2 or 8. So for a given separation of ions, the silicon-oxygen bond is 8 times stronger, making a very strong and resistant material. Strong SiO bonds are extremely common in nature. They form, for example, the mineral quartz, SiO2, which forms beautiful crystals. These are the power crystals you may have heard about. But quartz also, because it's so resistant, forms beach sand, and sand grains are typically grains of quartz. SiO bonds also form window glass, and they form in many ceramics and pottery that we have in our day-to-day lives. Very strong bonding indeed. There are many other ways to play this game as well. Aluminum, for example, is element 13. On the periodic table, you'll see aluminum right next to silicon. Aluminum wants to give up 3 electrons, and it bonds with oxygen, which wants to gain 2 electrons, in a ratio of 2 to 3, Al2O3. Al2O3, or corundum, is an incredibly strong mineral. It's used as an abrasive in many applications. Also, in its colored varieties, called ruby and sapphire, corundum makes a beautiful gemstone, a hard, durable gemstone that's greatly prized. Now, as you might expect, the distinctive character of ionic bonds leads to distinctive properties. And I want to look at 3 of these kinds of properties. I want to look at strength, at transparency, and electrical conductivity. Ionic bonds feature very strong and very directional bonds. That is, you have bonds between 2 point charges. So there's a direction in space where those bonds exist. Now you can think of these bonds as rigid sticks, like Tinker Toys, that if bent too far, they're going to break. You can see this anytime you've ever dropped a ceramic mug or a cup. If you take a cup and drop it on the floor, it smashes into tiny pieces. But those pieces retain their original shape because of the rigid bonding. And in fact, if you take the cup and the fragments, you can actually often glue those pieces back together and use the cup again. This is because ionically bonded materials are both strong and brittle. Now let's talk about optical properties. Light waves scatter off materials because of their electrons. In ionic bonding, all the electrons are tightly locked to one atom or another, so there are not a lot of free electrons around to scatter light. As a result, many ionically bonded materials are transparent. Window glass, for example, the mineral quartz, and many others are transparent to light, a feature of ionic bonding. Okay, and what about electrical conductivity? Once again, all the electrons tightly bonded, tightly held onto, so there are not a lot of electrons free to move around the material. And as a result, ionic bonded materials make excellent electrical insulators. Indeed, you may have seen the old glass or ceramic insulators that were once common on telephone poles to protect wires from grounding. Okay, now we come to the second kind of chemical bonding, metallic bonding, which is very different indeed. In metallic bonding, atoms adopt the strategy of sharing electrons. This behavior is quite distinctive from ionic bonds in which one atom takes an electron and the other one gives it away. I want you to think about a large collection of sodium atoms. That's element 11, and every one of those atoms wants to get rid of an electron. So when a bunch of sodium atoms come together, that's exactly what they do. They all give up electrons, and they form a sea of negative charge, of free-floating electrons. And in that sea, there are positive centers, the sodium atoms themselves, dispersed around that negative sea. The negative sea holds the positive charges together, and that's how metallic bonding works. Metallic bonding in nature is extremely common. If you look at the periodic table, almost all the elements that are on the left side of the diagram are metals. Those are all elements that want to give up electrons. And indeed, it turns out that about 3/4 of all the elements in the periodic table turn out to be metals. Elements can occur as metallic, but they also can combine with each other, and virtually any combination of two metallic elements forms an alloy, which also displays the properties of metals. There are many famous kinds of metallic alloys, and I'm sure you've seen many of these. For example, brass is a very beautiful alloy of copper and zinc, and is used for many beautiful artifacts. It's been known for hundreds of years, and many antiques of brass are found, as well as my own favorite, the brass musical instruments. We also have bronze, which is an ancient alloy of copper and tin. Then there's pewter. Pewter was used throughout the colonial period in America and in Europe. It was commonly used to form cups and plates and other sorts of everyday items. It's formed from the metals tin and antimony. Now, it's intriguing, in spite of the fact that pewter was very common in America, there was no North American source of tin. There were no tin mines in spite of North America's great mineral wealth. So all the tin had to be imported in the 18th and 19th century. We have many modern alloys. Steels, for example, are alloys of iron and carbon, with lots of other elements thrown in, sometimes as many as 20 other elements, titanium and vanadium, manganese. And these other elements provide steels with very special properties. The specialty steels is a huge industry in this country. And then we have modern transportation alloys, the lightweight aluminum and magnesium and titanium alloys that are used so often in our cars and our planes and other kinds of transportation. Now, if you think about Newton's second law, that's all the way back to lecture 5, you recall why a lightweight alloy is so important. Newton's second law says force is equal to mass times acceleration. And you can manipulate that equation and say acceleration, how fast you can accelerate your car, for example, is equal to the force over mass. So if you want a large acceleration, you either can have a big force, a big engine, or else you can have a lightweight automobile. And that's where lightweight alloys come in. Now, metallic bonds have a number of distinctive properties. Again, let's look at strength, at transparency, and at electrical conductivity. The bonds between positive atoms in that sea of negative charge aren't particularly directional. So you can actually take metals and bend them. In some cases, as in gold, you can actually hammer them out into paper-thin sheets. The process of gilding, which is still a trade practiced by artisans, takes chunks of gold, you hammer them paper-thin over and over again, and then apply that paper-thin sheet of gold to surfaces. For example, the beautiful golden domes of many of the state capitals in North America. Now, in terms of optical properties, that mobile sea of electrons scatters light, so metals show a metallic luster, that shiny luster. Indeed, if you can take a piece of glass that's very smooth and coat the backside of the glass with a metal, you get a perfect reflecting surface called a mirror. And finally, metals make wonderful electrical conductors because of that sea of electrons. The electrons are free to move, and so electricity can pass through metals quite easily. Now we come to the third bonding strategy, the covalent bond, which, like metallic bonding, involves sharing of electrons, but in this case only locally with a few atoms. I want you to think about what must happen when two hydrogen atoms come together. Hydrogen is element 1, and so it has 1 electron. So each hydrogen atom wants to see 2 electrons. And what happens in covalent bonding is exactly that. 2 hydrogen atoms come together and they share their 2 electrons collectively. this forms an H2 molecule, and H2 is a gas that can occur in our atmosphere. Now, this link between the two hydrogen bonds, the shared electron bond, is called a covalent bond. Now, this bond contrasts with a hypothetical hydrogen-hydrogen bond that could be ionic. Imagine, for example, two hydrogen atoms coming together and one takes the electron from the other one. So you have an H2 molecule, but with a positive charge and a negative charge in two ions. That's not what happens. Imagine also that you could have a hydrogen metal in which every hydrogen gives up its electron to a C, so you have a negative C with positive protons, the nucleus of the hydrogen, floating around. And that doesn't happen either. You get a covalent bond. Covalent bonds occur in many, many different kinds of materials. For example, in the atmosphere, the most abundant gas, nitrogen, N2, has a covalent bond between two nitrogens. Oxygen that we breathe, O2, has a covalent bond between two oxygens. Another example, a very important example, is water. In water, you have two hydrogen atoms, each of which wants to have two electrons, but only has one. And you have an oxygen atom which has 8 electrons and wants to have 10. And the strategy here is so simple. The hydrogens say, I want 1 extra electron, I'm going to go near that oxygen to find it. And the oxygen says, aha, each of those hydrogens has 2 electrons, now I have my full complement of 10. And you form an H2O molecule in which every atom is happy. The most versatile of all the covalent bonded elements is carbon. Carbon is element 6, and its strategy is to gain 4 more electrons. It often achieves this state by linking to 4 other atoms. The simplest of these ways of doing this is to find 4 hydrogens. And so you have a carbon surrounded by 4 hydrogens. CH4 is methane, or natural gas. In this case, each hydrogen shares 1 electron with carbon, and carbon sees all 4 of the hydrogen electrons and so has a total number of 10. Now, as with ionic bonding and metallic bonding, the properties of materials with covalent bonds reflect the behavior of their electrons. First of all, you're forming small molecules, and small molecules typically form liquids or gases because they're light, they're moving around, and they fly off into space or form very liquid type arrangements. Also, in terms of electrical conductivity, since all the electrons are shared locally and not through the entire material, covalently bonded materials are often very good electrical insulators. Indeed, we use covalent bonded materials for electrical insulators in our daily lives because ceramic materials, the ionic bonded materials, are brittle. They break, and you want a wire to be flexible. And so you use a covalently bonded material to surround your metal wire. Well, to summarize this lecture, we've seen first that chemical bonding results from the curious fact that atoms with certain key numbers of electrons, that is 2 electrons or 10 or 18, are particularly stable. Chemical bonding is a strategy to achieve a stable number of electrons for every atom involved. And so we have seen the 3 common types of bonding. Ionic bonds are those in which electrons are transferred from one atom to another on a permanent basis. This produces ions which attract each other and therefore bond together by electrostatic forces. We see metallic bonding, in which every atom gives up electrons to form a negative C, and that negative C holds together the positive charges, the individual atom centers that form the metal. And finally, we have covalent bonding, in which just 2 or just a few elements come together, and they share their electrons so that every atom sees the magic number that it wishes to have. Now, in the next lecture, we're going to explore the incredible covalent bonding chemistry of carbon, which is the most versatile of all the elements, the most fascinating of all the chemical elements.